Hello everyone and welcome to my channel. In this video I'm going to talk about AVL trees, a very special kind of binary search trees. So let's see what AVL trees, but at the first I'm going to talk about the need to have some trees like AVL trees. So with this two examples that you see here, the tree number tree A and the tree B, I'm going to say the need to have some trees such as AVL trees or red-black trees, in which we call the self-balancing trees or the trees that are balanced. So there is a need for that, and I'm going to show using the one of the main operations in a binary search trees, which is the search operation. If you look at the tree A, we see that if we want to find number or the node 2, which is the very last node of the tree, which is the one which is at the very bottom of the tree A, we need to do exactly n search operation, which is n is the number of nodes that we have. In this example, both the tree A and tree B, we have 5 nodes, so n is equal to 5. And as you see, for finding the node 2 in the tree A, we need to do exactly 5 searches. So first we need to search 15, and then go to 12, and then 10, 7, and at the end we're going to have number 2, which is from the big of n, as you see in the worst case, big of n. Here we're not talking about the best searches for the tree A and tree B, and the reason is that the best search is always going to be big of 1, and that happens when we're trying to find the item which is located at the root. However, as you see in the worst case, what's going to happen is that if like the node 2, which is again the furthest from the root, we need to do search search operation. However, in the other tree with the same data, as you see, we have number 15, 12, 7, 10, and 2. We only need to do 3 searches. So we're going to do 12, and then 7, and then 2. So there is only 3 searches, and compared with 5 operations here. So you might say that the 3 searches and 5 searches are not that much different. However, if you look at the differences when the n becomes a large number, the difference becomes even more obvious. For example, when n is equal to 1000, with the trees like this, that it grows only on one side, either the left or right. So we might have also some trees that growing only on the right side. Then we need to do about 1000 searches. However, if the tree is balanced, which means that each node except the leaves have two children, or about 2 children, then the search operation will reduce to the log of n in the base 2. So for n equal to 1000, the number of search in maximum will be 10. And compare 10 with 1000. And for sure, even 1000 is a small number. You can imagine like the trees with like the hundred thousands of like the nodes and millions of nodes, and you can see the difference between the log of n and the n very clearly in these cases. But when we if you have noticed, I mentioned like the tree is balanced. So let's see that what balance means and how we can actually measure that if a tree is balanced or not. So here is the definition of a balanced tree. A binary search tree is balanced if the difference between the height of the left side and height of the right side is either 0 or 1. So that's what we call the balanced tree, and that's for any node that we're talking. So if you look at the node 15 on the tree A, you see that the right side, the height is 0 from the right side, and the height from the left side is 5. So for sure, the node 15 is not balanced. Same thing for the node 12, 10, and these nodes are not balanced, although the nodes 7 and 2 are balanced, because the difference between the height of right side and left side are for the 2 is 0, and for the 7 is 1. Usually in like a textbooks, the reference books, you might like see that they're using the like the height of the right minus like the height of like the left side, and if it's positive difference, then that means that the trees has grown from the right side. If it's negative, it means that the tree has grown from the left side. So I'm going to write the balance factors. The balance factor is the difference between the height of the right side and the height of the left side. For the tree A, here the balance is 0 for the node 2. That means that, as you see, on the right side the height is 0 and the left side also 0. For the node 7, it has not grown from the right side, so from the right side its height is 0, 0, but from left side, as you see here, it is 1. So 0 minus 1 going to be negative 1 is the balance factor of 7. Then we have 10, which is, as you see, on the right side doesn't have anything, so on the left side it has 2, so the path from 10 to its very left child is 2, so it's going to be 0 minus 2, so it's going to be negative 2. For the 12 and 15, it's going to be negative 3 and negative 4, so that's going to be the balance factors. However, if you look at the 3B here, 10 and 2 both are going to have like balance factor of 0, same thing for 15, because again there are leaves, and leaves all the time have the balance factor of 0, the difference between right side and height of the right side and height of the left side. The balance factor of 7 also is 0, and you might ask why, because as you see, the distance or the height from the right side of the 7 is 1, and from the left side also it is 1, so the balance factor will be 1 minus 1, which is 0. For the node 12, as you see, it has grown 1 from the right side, and from the left side it has 2, which is, as you see, here is 1, here is 2, or you can see this is 1 and also 2. So on the right side is 1 and the left side is 1, so 1 minus 2 is negative 1. And as you see here, the 3B is balanced, because every node either has a balance factor of 0 or a balance factor of 1 or negative 1. And usually we're talking about the absolute value, so the absolute value of the balance factor should be 0 and 1 in order to call it a tree balanced. So that's the main reason that we need to create or have like the trees which are self-balancing, or at least there is a mechanism to make these trees balanced. So when we're going to see that, when does this happen that the tree goes unbalanced? Usually this happens when we're deleting a node or we're inserting a new node. That's when like the trees might like to grow or might like to shrink, and that's we need to just to use some self-balancing like the tools in order to fix that. And one of these trees that we're going to learn today, we're going to be AVL trees, which the balance factor of like each node or of the tree is either 0 or 1, and again we're talking about the absolute value. If not, the balance factors are either 0 or 1 or negative 1. Now let's take a look at how we can actually calculate the balance factor. In order to calculate the balance factor, we need to calculate the height of the root and its left subtree and its right subtree's height as well. So here is the pseudocode, or very similar to the actual Java code, of how we can recursively calculate the height of a node. So assuming that we're assuming the node n as a parameter, we're going to return an integer which is the height of that node. So it starts with checking that if the node n is equal to null or not. If it is, return 0 means that there's no height because the node does not exist. If the node exists, then the height of that node from the left side, we're going to see it, how far it can go from the left side, is going to be 1 plus, because we're having the node n, plus the height of its left child. So that's what you see here, this expression here. So 1 plus the height of n dot left, and again 1 is because we're including the node n after calculating the height of its left subtrees. And then same thing for calculating the height of the right subtree of the node n. So it's going to be 1 plus the height of its right child. That's going to be the height of the node n from the right side. Then the height of the node n will be the maximum of these like these two numbers. So with the one that is larger, it's going to be returned as the height of that node. So look at this example, or these three T that we have here. The node that you see here, maybe it's good just to also name these nodes. For example, A, B, C, D, F, G, H, and the node I. So the node I, so which in this case is the node N, as you see, it's not null and it doesn't have any left or right child. So the left height and right height will both be equal to 1, and the maximum of that one, 1 and 1 will be equal to 1. So the height of this node I will be equal to 1. Same thing for the node F, E, and D. All of them will have the height of 1. So here where again these colors in red specify the height of a node. Then let's look at the node H. The node H, as you see here, as the pseudocode or the algorithm says, is not null, so we need to calculate its left height, which is 1 plus the height of its left side. Because its left side is empty, it doesn't exist, so it's 0, so the left height will be 1. So I'm going to keep number 1 for the left side of H. And then on the right side, as you see, it has the node I, which has the height of 1. So 1 plus 1 will be 2, and the maximum of 1 and 2 will be 2, and that's exactly true. As you see, the node H and its right side, they are making 2 nodes. Let's go to the node G. The node G, again on the left side, doesn't have any, so from the left side it's 1. However, on the right side, it has the node H, which has the height of 2, plus another 1 here is going to be 3. So the height of G also will be 3. So let me also delete the extra numbers here to avoid any confusion. So here we have the height of 3 for G. Now let's take a look at the node B. The node B on both sides, left and right, has the height of 1. So that's how far it went. And then plus itself, so it's going to be 2 both from the right and left side. So the maximum of 2 and 2 will be equal to 2. Now let's take a look at the node C. From the left side, the node C has only one node, which is the node F. And so the height of F is also 1. So from the left side, this height of C is equal to 2. However, from the right side, the height of C is equal to 3, which is the height of G. And we're going to add 1 to that one. It's going to be 4. So the height of C will be equal to 4. And now we're going to look at the height of the node A. So the height of the node A, okay, again, as you see, is a recursive call. So we're going from the very bottom down to calculating the height of the node A. So it's like the bottom to up, like the calculation, because it's recursive, that goes from the very bottom of the tree up to the very top of the tree, which is the node A. And now that we have calculated the height of the node C and B, which are the immediate children of the node A, we're ready to calculate the height of A. So from the left side, the child of A, which is B, has the height of 2. Okay, so it's the height of 2. And then so from the left side, the height of the A will be equal to 3. And now from the right side, as you see, C has a height of 4, so plus 1 is going to be 5. So between 5 and 3, 5 is the largest number. So that's going to be the height of the node A. So as you see here, this example specifies the height of the nodes A, B, C, and again, all the nodes in tree that we have here. Now that we have calculated the balance, the height of each node, and especially specifically the height of the root node, we're going to see that how we can actually calculate the balance factor, and that's the formula, or in other words, the algorithm to calculate the balance factor. So if the node is null, it means 0. Otherwise, the balance factor is the difference between the height of the right child, or from the right side, and the left side. Okay, so we were able to easily calculate the height of each node with this recursive call. And as you see, to calculate the balance factor of any node, we still need to calculate or use the height function. So this height function that you see here has been called is the same as the height function that we have written here, which is a recursive one. So we need to calculate the height of the node from the left and right side, and the difference between these two will be the balance factor. So with the same tree that I have here, so I'm going to say here red color, I'm going to specify the height of each node, and I'm going to use the blue color here to specify the balance factor. So the blue color will be the balance factor of each node that we see, and we're going to see that which node is not balanced. So the node I, as you see here, its height from the left and right side, both of them is 0. So the difference between the right and left is 0. So the balance factor for the node I is 0. So as a rule, every leaf or each leaf in a tree has the balance factor of 0, because the height from both left and right is equal to each other, or equal to each other. So that means that the balance factor for all leaves are equal to 0. So no need to calculate the balance factors or easily for the nodes. We can easily find that. Now let's take a look at the balance factor of H here. So as you see here, from the right side, the height of the like the H is 2. However, from the left side it is 1, because 0 is the height from the left child. We're going to add it 1 that we have here in the formula as you see here. So it's going to be 2 minus 1, which is going to be 1. And it makes sense, as you see on the right child, node H goes 1 down. From left side it doesn't go anywhere. The node G, as you see from the right side, it has a height of 3. Okay, but if you just look at the left side, it has no child. So 0 plus 1 is going to be 1. So the height, the balance factor of G will be equal to 2, which is 3 minus 1. Now we're going to take a look at the node C. From node C, from the left side, as you see again, look at the formula again. The height from the if left child is 1, so 1 plus 1 is going to be 2. Again, this is from the left child, and from the right child it is 4. So 4 minus 2 will be equal to 2, and that means that the balance factor of C is this number. Now take a look at the node B. Again, as you see from both sides, it has grown same like the degree. So from right side its height is 2, from the left side its height also is 2. So 2 minus 2 is going to be 0, so that means that the node B is balanced. Now we're going to take a look at the node A. The node A from the right side has a height of 5, but from the left side it has a height of 3. So that means that the balance factor of A will be 5 minus 3, which is going to be equal to what's going to be 2. So let's see that what or how we actually got this number. Let's take a look at it again one more time, and look at the node A. As you see here, if we want to go from A to node B, we need to pass 3 nodes. The node A, then we need to go node B, and then to node D. See, which are 3 nodes here. However, if we're going to visit the node I, which is the rightmost child of the node A, or the grandchild of A, we need to go, so this is from the left and from the right. We need to go from A to C, and then G, and then H and I. As you see, there are 5 nodes. So 5 minus 3 is the difference between the nodes, like the height or the left from the right and left. So that's equal to 2. So that's how it works. The height of a node, so which is we're calculating the height of its left and right child. We're adding 1 to that one because we're including the node that we're going to calculate its height, and then we're returning the maximum number. To calculate the balance factor, however, after calculating the left and right subtree's height, we'll just return the difference, because we want to see that how much it is balanced. Okay, how much is the difference between the growth rate or the growth of the right child or right side of the tree and the left subtree of that node. So after learning the balance factors and also height of like a node, we're going to see that how we can actually write or create AVL trees which are self-balancing and not fix the problems if exists when we're inserting a node or when we are deleting a node. Okay, now we're going to see different type of rotations that we need in order to balance the AVL trees. As I said before, AVL trees are binary search trees, but the special ones which are balanced, which means that they're going to make sure that the search operation or insertion or delete operation in trees will be efficient, and it's going to be like the in the big O of log of n, in the average and also in the worst case. So let's see that how it works. Here you see 4 scenarios that can happen, and here if you look at the numbers, I said assuming that we are trying to insert 3 numbers, A, B, and C. In all of these cases that you see here, A is less than B and B is also less than C. So that also means A is less than C as well. So there is one case that we have this combination on the very left, which is we need to do a left rotation. So as you see, because it is a binary search tree, B is on the right side of A and also C is on the right side of B. And here I'm going to write the balance factor of each node. So the balance factor for the node C is 0 as it is a leaf. So I can also do for all other trees as well here. The balance factor of the node B is 1 because its height from the right side is 1, but from the left side is as 1 plus 1 going to be 2. From the left side, its left child has a height of 0, so 0 plus 1 going to be 1, so 2 minus 1 will be 1 as a balance factor of B. Now the balance factor of A will be the difference between the height of A from the right side and its height from the left side. From the right side, the height of A is equal to 3, but from the left side, its height is 1. Again, 0 plus 1 because that's the height of its left child, plus 1, which because we're going to include node A. So 3 minus 1 going to be 2. And as you see here, this is a positive number. So when we have positive numbers, so 2, B, C, as you see, or another one, if you see this all growing in one side, we only need to do, and again, if if all the nodes are growing in the right side, okay, and this like a direct path, then we only need to do one single left rotation around the like the node B in this case. So we're assuming that we just inserted the node C. So in case you were asking that what is the order how we end up with the node C here, maybe we have inserted the node A first and then B, and now we inserted node C that caused the tree become unbalanced. So with the one single rotation around B, we're gonna fix the problem. Let me also delete this like the arrow here. So with one single rotation around, so left rotation around B, it's gonna fix. So it's gonna be B will be the parent of A, and as you see here, B was the right child of A, and now A will be the left child of B. Okay, and there is no change on C because here the A was the node that had problem. So again, B was the right child of B, and now it became the left child of the A. And let's now look at the balance factor of the new case of, or new status of the tree. The balance factor of C is 0, the balance factor of A is 0, both of them are leaves, and the balance factor of B is also 0. And the reason is the height of the B from the right side is 2, from the left side is also 2, so 2 minus 2 is 0. And we fix the problem of having the trees are which of the nodes which are unbalanced. So even if you look at this part of the trees that we have here, you see that with this one to find the node C, we had to do 3 searches. But now we need to do at most 2, so we only search B and then we can find the node C. However, before we had to do 3 searches, so we already see the the picture. Now let's go to the right rotation of the like the tree and the cases it happened. So again, the node C is greater than B and B is greater than A. Again, the balance factor of A is 0. The balance factor of B is -1 because from the right side its height is 1. From the left side it is 2. So 1 minus 2 is -1. For the node C, from the right side its height is 1, but from the left side it is 3. So 1 minus 3 is -2. So in the cases that the tree grows in one side and from the left, we only need to do one single right rotation around again the node B that we have in around the node that is the parent. So again, here can be a scenario that how we end up with the tree like this. Maybe let's we have inserted C first and then the node B, and then we inserted the node A that caused the tree to be unbalanced. So that leaves this part of the tree. Now one single rotation around the node like the B, we're going to create this one. So B going to be in there as the root, and then here as you see, B was the left child of the C, so that means that C now is going to be the right child of the B. So again, it was the right child of C. Now C, because B was the left child of C, and now C will be the right child of the B, which is exactly opposite. And again, if you see, all the balance factors are 0. Now look at the third case, or the third scenario that can happen, which is we have inserted maybe this node C and then maybe in the node A, and then we have inserted node B. So the node C for sure is greater than both A and B, and as you see here, because B is greater than A, so B is on the as the right child of A. In this case, again, let's write down the balance factors. So we have 0 for B for sure because it's the leaf. For the A, we have the balance factor of 1, again because from the right side it has a height of 2, from the left side it has a height of 1, and again the balance factor for C also going to be -2 because from the right side it is it has no children, so its height of left children is 0, so 0 plus 1 is going to be 1, and from the right side, from the left side it is 3, so 1 minus 3 we're going to be -2. In this case, that the trees grows, but not in direct like the one straight path, but it just goes here and then here, something like that. So it goes first to the left and to the right. We need to do one left rotation around A first, and then we're going to do one right rotation. So let's see how it happens. So first we're going to do the left rotation. So left rotation around A. So we're going to have the node C here, and then here's going to be the node B, and then here we're going to have the node A. So that's going to happen. So it's going to be a left rotation. So that's now see the balance factor. So B 0, A 0, B is -1, and C -2. As you see here, this case that we have here now is exactly the case or the scenario number 2. So let's just put numbers: scenario number 1, scenario number 2, and scenario number 3, and the last one is the scenario number 4. So as you see, after one left rotation, we actually ended up with the scenario number 2, which is just simply doing a single right rotation. So it's going to be B, and again the C and A, again all with the balance factor of 0. So that's how it works with the left right rotation if we have like a case like this. The fourth scenario, where we need to do a right rotation first and then one left rotation in order to fix it, can be happen like this. We have the node A inserted, and then we have inserted node C, which is greater than A for sure, and then we're inserting the node B, which is less than C but is greater than A. So as you see here, it is not growing the the straight line. So it first grows in the right side, and then it grows in the left side. So here we need to do one right rotation first around C again. So it's going this way. So again, let me delete the unnecessary stuff here. And then after this rotation, we're going to end up with A. Here we're going to have the node B, and here we're going to have the node C. So again, as you see, B was the left child of the C, and now C became the right child of the B. Now, if you look at this tree that we have here, A and B, C, and it's just has grown from on the right side, it is exactly equal to the first scenario that we have, which was only need a left rotation. So doing one left rotation around B, we're going to end up with B, and then here we're going to have A, and here we're going to have the node C. So these are all the cases that can happen. So either the very straight ones, so the 1 and 2, which are gonna like go from again one direction, either to the right or to the left, or the cases that are growing in both left and right, and we have to do 2 rotations. In this case, that it goes to the left and then to the right, we're gonna do one left rotation and then right rotation. If it goes first to the right and then to the left, we're going to do one right rotation first, and then we're going to do a left rotation to fix the problem. So after this, I'm going to show you an example of like inserting some numbers in AVL trees, and how we're going to show these some of these scenarios, at least maybe 2 or 3 of them, that how we can just fix the AVL trees and how it's going to balance itself. Now let's take a look at this example. So I'm going to insert these few numbers that you see here into an AVL binary search tree, and I'm going to show you how it works and how it can actually balance itself. So I'm going to start with the very first number, which is 10, and we're going to insert number 10, and because there's no other node in the tree, number 10 will be the root. So here is the tree, and the root is 10. After that, we're going to insert number 15, and because number 15 is greater than 10, it means that it should go to the right side, and because there is no other node, number 15 will be their immediate child, right child of the node 10. After that, we're going to insert number 18, and because 18 is greater than 10, we need to go to the right side, and because it is greater than also 15, we need to insert it here as the right child of 15. So here is the trees that we have. As you see here, the tree is not balanced anymore. So the balance factor for 18 is 0, for the 15 is 1, and for the 10 it is 2, which is gonna show us the very first case that we need to do a left rotation around the node B, which is the node 15. So after the one left rotation, we're gonna have these 3 in this case. So we're gonna have 15, and then here we're going to have the node 18, and then here we're going to have the node 10. So as you see, the tree is a still binary search tree. However, the tree is balanced. All the balance factors are equal to 0, because as you see, the node 18 and 10, both of them are leaves. So balance factors are 0 for 15 because it grows the same amount of like the height from the both left and right side. So the balance factor is also 0. So after inserting number 18, the tree will self-balance itself, and it's going to create or like to put this tree to be in this status. After number 18, we're going to insert number 5, which will be, because it's less than 15, it's going to go left side of 15, and because it's less than 10, it's going to be, the left side of the 10. So we're going to have the tree in this one here. I'm going to add number 10, and here we have 5. So let's write the balance factor. So is 0 for the 5 and 18 because they are leaves. For the 10, the balance factor is -1, again because the difference between the height of the right and left is -1. For the 15, the balance factor is also -1 because again the difference between the height of the right child and the left child, it is 1, but because we're deducting left child minus the from the right height, was going to be -1. So far so good. There's nothing to there's no need to do any rotation because the tree is balanced, is not either 2 or -2, so there's no need. And after that, we have the number 3 that we're gonna insert. So we're gonna insert number 3, which is again will go here because it is less than 15, less than 10, and less than 5, and less than 3. If you look at the balance factors now, maybe it was better actually to draw it in another case here. It was maybe better. So I'm going to have 15 here, and then here I'm going to have 18, 10, and then we had 5, and then we have 3. So the balance factor for 3 and 18 is 0 again, because both of them are leaves. For 5 it is -1, for 10 is -2, and for the 15 here is also -2. So we need to fix the tree here as you see we have it here. So we need to do one like the rotation around the 5 you see here, one right rotation. If you look at this example that we had, the one here that we had to the right rotation. So this is scenario number 2. So we're going to do in one rotation, and that's going to be 15. It's going to be 18, and that's going to be then 15, and it's going to be 10, and that's going to be also 3 is inserted here. So the balance factor are going to be 0, 0, 0 for 15, and for the this actually was I wrote one of the numbers wrong. I need to just fix that. It is actually 5 and not 15. So here we have 5 and 15. So the balance factor 5 is 0. For the 15, the balance factor is -1 because the difference is -1 between the right height and the left height. So after that, let's say we're going to insert the number 7. So number 7 will I'm going to write it here. So inserting now number 7, we'll go here. So we have 15. Then we have 18 here as the right child of 15. Then we have 5. We have 10. Here we have 3. And then number 7 will go to the left side of 7. Again, it's a binary search trees, and you know that. You can again watch my other videos about this is stuff about how the binary search tree works. So let's write the balance factors. For 7, 18, and 3, the balance factors are 0 again because there are leaves. For the 10, the balance factor is -1 again because the difference between the right and left height sub 3. For the 5, the balance factor is actually +1, and it is because, as you see here, it's right from right side it has a height of 3. From the left side it has a height of 2, so 3 minus 2 is going to be 1, so it's +1. Now let's see the balance factor for 15. Again, from the right side, 15 to 18 there are 2 nodes, but from 15 to maybe the node 7, which is the very bottom of the tree, it is 4 nodes, so 4 minus 2 is going to be 2. So and because we were left minus right minus 1 is going to be -2. So 2 minus 4 actually is going to be -2, which is, as you see here, the node 15 is not balanced. So let's see that which scenario it is. It's like the complex one here. So if you look at this one, you see one that goes to the left, so from 15 to 5, and then from 5 to 10, which is going to right. So it's going to be I think the third cases that goes to the left first. So that we're going to do a left rotation, and then we're going to do a right rotation. So the left rotation going to be around the node 5. So that's going to happen. Okay. So here is going to be the node 15, and then there is no change here for the node 18, but going to be for the node 5. So now that because we're going to do the rotation around the node like the 5, so 10 will be the parent of the 5, and 10 which was the right child of the 5, and now 5 is going to be its left child. So here we have 5, and then here we have 3, and then there is no now we need to do something about the left child of 7. Left child of 10. So the left child of 10 now will be the right child of like the 5. Okay, so let's just review what we did here because it's like a little complex, So look at the third cases here. So we did one left rotation around 5. Okay, so that means that 10 will be now the parent of 5. So 10 was the right child of 5, and now 5 we're going to be its left child. So now because 5 became the left child of 7, so 7 cannot be the left child of 5 anymore. Okay, so keep that in your mind, and then look at what we had here. 10 was the right child of 5. So now it's like the trade. We just gave up the right child of 5, right? And now we need to give it another right child. Okay, so that's how we are giving up the left child of 10, okay, which was 7, and instead we took 5, and now we're again just doing a trade. So let's see what happened. So 5, I'm going to write here, gave up its right child, which was 10, so needs a new one. And also 10 gave up its left child, so needs a new one. So the left child of 10 now became 5, right? So we're done with this one here, and 5 gave its right child was 10. So what it needs a new one, which gonna be the left child of 10. So now here is that it works. I hope that this explanation clarifies how we did this one and why numbers like the node 7 became the right child of 5. So let's write the balance factor for these nodes. So we have 3, 7, and for 18 is going to 0. For the 5 also is going to be 0. Now for the node 10, as you see here, is going to be -2 because the difference is again right and left. For the 15 also is going to be -2. And if you look at this one here, now we have this case here, which are all on the very left. Which, if I'm not mistaken, is going to be the scenario number 2, right? That we need to do one right rotation, and again, that's what it was expecting. So that's going to be, again, one right rotation. So one right rotation around the node 10. So we're going to have the 10 to be the parent, and now 15 is going to be here, and then we're going to have 18, no change here. And still we're going to keep the left child of 10, which is 5, and then here we had 7, and where you had number 3. So again, number 10 gave up, if number 15 gave up its, left child, so it's going to get the right child of 10, which, as you see, does not exist, so that's fine. And number 10 became the parent of the node like the 15. So let's write the balance factors. You see for 3, 7, and 18, those are 0. For 5, it is 0 because, again, the difference between right and height subtrees are 0. For the 15, it is 1 because from the right side we have node 18, but from the left side we don't have any node. And the balance factor for 10 is also 0. And again, if you look at the reason, so from the right side we have the nodes 15 and 18, okay, which is going to be height of 2, plus another one which the node itself is going to be 3. The node 10, okay, from the left side has the node 5, which has the height of 2, and when we add 1 to have the height of 10, it's going to be 3, so 3 minus 3 is going to be 0. And as you see, all the nodes are balanced, either they are 0 or +1 or -1. So I think the last number that we wanted to insert, I need to go up here to look at all the last number was number 2. So I'm going to go here and insert number 2. This is going to be 10, and then we're going to have number 5. Here we have 15. Here we have 18. Here we have 3. Here we have 7. And here we have number 2. Okay, and we're going to just write down all the balance factors for this one. So for the 18 is 0, for 7 is 0, for the 2 is also 0. For number 3, the balance factor is -1. Okay, for the balance factor for the 5, it is -1 as well. Okay, because the difference again between right and left is 1. For the 15, it is +1. Again, on the right side, it has one node, which is 18. Left side, nothing, so it's going to be 1. For the node 10, the balance factor is -1, and the reason is the height of the tree from the right side, it is 3 for 10, which is 10, 15, and 18, so 3 nodes. And from the left side, it is actually 4 because the furthest one is node 2. So we need to do 4 like the steps 10, 5, 3, and 2. So it's going to be 2, 3 minus 4, which is going to be -1. As you see, all the nodes either have the balance factor of 0 or 1, also -1. So any of these 3 cases happen, and we don't have any balance factor which is either +2 or -2. And we should keep it in mind that anytime that we're doing balancing the trees at the end of all the rotations, the tree will be balanced. It means that there will be no node with the balance factor of either +2 or -2 after, again, all the self correction and self balancing. So here's an example for doing the AVL trees for inserting a node. The deletion also will be very similar. If you have questions or comment, please add it to the comment section. I will be happy to answer to your question, or maybe provide more examples of of the AVL binary search trees.